Hello, everybody. It's Miss Rector here to talk about nuclear reactions. So, gonna make this as short as I can, but it is a lot of information. So, here we go. Nuclear reactions. We're going to talk about alpha, beta, and gamma decay. I'm going to turn on my little pointer here and turn this off. Sorry. Okay. So we're going to talk about alpha, beta, and gamma and the process in nuclear reactions. Learn how to read those symbols. So, quick refresher on the atom. Atom has two parts. You have the nucleus, which has your protons, your positive protons, and your neutral neutrons. And then outside it, of course, you have the orbiting electrons. So, all matter, what do we know about the atom? We say all matter is made up of elements, carbon and hydrogen, things like that. The smallest piece of each element is called an atom. And atoms of different elements contain different numbers of protons. And the mass of an atom is almost entirely due to the number of protons and neutrons. Remember, electrons are so small we don't count them in our things. So then we learned about the nuclear symbols like this. So when you see a symbol written like this, that number at the top, that is your mass number. So that is equal to the protons plus the neutrons. The number at the bottom down here on the left is your atomic number. So that's, of course, the number of protons. The element symbol tells you what the element is. And if there was a charge, that would be up at the top right. So atomic number, number of protons and neutrons gives you the mass. The Z, that's the atomic number, tells you the number of protons. And if I take A minus Z, I can figure out the number of neutrons. So we've been doing this the past couple of days. Number of neutrons is equal to the mass minus the atomic number. So given two isotopes like this, they're both uranium. So this is uranium, uranium-235. This is uranium-238. They're both uranium. They both have 92 as their atomic number, which would mean they have 92 protons. So remember, this thing on the bottom is Z. I'll go to the next slide where it's all filled out. So they're both 92 for their Z's. Their masses are different, which means their number of neutrons is going to be different. So you take the mass minus the protons to give you the neutrons. So mass minus protons gives you neutrons. So the only thing different in these two uraniums is the number of neutrons. Oops. Most of the isotopes which occur naturally are stable. So if they occur naturally, they're probably stable. A few naturally occurring isotopes and every single man-made isotope are unstable. So if you have an unstable isotope, it can become stable by releasing different particles. So this is where the nuclear reactions happen. This is called radioactive decay. And the elements which undergo this process, we can call them radioisotopes or radionuclides. Now, when you think about, there's four fundamental forces in nature. So you're probably very familiar with gravity, force of gravity, and the electromagnetic force. But some of the ones you haven't talked much about are the nuclear forces. And that's because gravity and electromagnetic force, you can see these effects in your everyday life. But things like the strong nuclear force only happen over very small spaces, like inside the atom. So we know that the positive charges repel each other, right? And there must be something holding all these protons and neutrons together. So that is what we call the strong nuclear force. And again, why haven't you ever learned about this in physics up until now? Probably because it's only significant between subatomic particles. So it doesn't affect you in, your everyday life. A neutron, which has no charge, also helps kind of lessen those repulsive forces between protons. So neutrons are kind of like the glue helping to hold those protons together in the nucleus, along with, of course, the strong nuclear force. So for about the first 20 elements, a stable atom is going to have about the same number of protons as neutrons. So you've probably noticed this the past couple days when we're calculating neutrons for things like oxygen 16, right? You're like, oh, 8 protons, 8 neutrons. And a lot of people tend to think, oh, well, you have the same number of protons as you do neutrons. But no, that's not true. Once you get beyond the first 20 atoms, you kind of need more neutrons to make it stable. So you need more glue in there to hold things together. And once you get past 83 protons in the nucleus, there just aren't enough neutrons to help keep it together for long. So everything above 83 on the periodic table is going to be radioactive. Nuclei with too many neutrons can also be unstable and emit beta radiation. So let's figure out what these alpha, beta, and gamma things are. So you can either have an alpha particle, which we symbolize. This is the little symbol for an alpha. So kind of like a sort of draw it. When you're drawing it, I kind of go for that little, Jesus fish looking symbol. And then there is the beta symbol. Symbol for a beta particle looks a lot like a bee, right? It's just got kind of a little tail. So that one's usually easy to draw. And then there is the gamma ray. So gamma ray is not really a particle. It's more radiation, like light energy, think. The symbol for that, kind of think like a cursive Y thing. So it's got a little sort of loopy down here, Y. So let's talk about alpha decay. An alpha particle is identical to a helium nucleus. So this is basically a helium nucleus. There's no electron flying around it, right? It's just got your 2 protons and 2 neutrons. So when we talk about Rutherford's gold foil experiment, this is what he was shooting, an alpha particle at that gold foil, or alpha particle ray gun. It contains 2 protons, 2 neutrons. So we are going to write these nuclear reactions in this sort of format. So this would be the first element with its mass and its atomic number. If it emits an alpha particle, so what's going to happen after the reaction? You're going to have an alpha particle released, and then you're going to have some new element with a new mass and a new atomic number. Now remember, whatever is in the beginning should be represented in the end. So these 2 numbers should add up to your original mass. So A minus 4 plus 4 should give you A. Z minus 2 plus 2 should give you Z. So the protons here are going to be 2 less than the protons here, because this alpha particle coming out of here is going to steal 4 from the mass, 2 protons and 2 neutrons. So that's alpha decay. You have this unstable atom. It emits an alpha particle to become a more stable atom. Still maybe not stable, but more stable than this one. So here it is in a different format to show you. So here if we have radium and 226. So here this one has a mass of 226 and 88 of those are protons. So once it emits this alpha particle, 2 of the protons went away and 2 neutrons went with it. So now you have Rn, 222, radon 222, and that has 86 protons because 2 of them went down here, and the mass went down by 4 because you lost 2 protons and 2 neutrons. That's alpha decay. So we write the symbol, and the equation would look like this. Ra, 226, 88 protons. Helium nucleus comes out. There's your alpha particle. So you could write, by the way, that little alpha symbol if you wanted, or He, either one. And you lost 4 from the mass, so this went down to 222. You lost 2 of them were protons, so that went down to 86. So what should happen is if I gave you this and said this undergoes alpha decay, you should be able to write this, predict what is going to be created, and finish this equation. Here's another one. So again, I'm not going to spend a huge amount of time on this. That A should be up here. So to figure out the mass of this new thing, you'd say 222 minus 4, so I'd get 218. I'd say 86 minus 2 gives me 84. And then I'd go to the periodic table and look up what has the atomic number 84. Oh, it's polonium, and put that in there. Okay, so you just figure out, well, what's the new mass going to be? What's the new atomic number going to be? And then I can figure out what the new element is. So again, some more examples here. What did it start with? Let's look at that. These two things, if you added them together, should give you 234. Boom. These two things, if you added them together, you should get 92. So that would have been uranium. So if you know the skeleton equation, then you should be able to solve for either one of these. If you were given one, you should solve for the other. So again, if I was given this and said it undergoes alpha decay, you say, okay, let's write my alpha particle over here. This minus 4 is going to give me 226. 90 minus 2 is going to give me 88. Now I'll go to the periodic table, look up 88, and figure out its symbol. So we just have more examples of these that if we were in class, we would work out, but you can pause here and work it out if you like. All right, let's talk about beta decay. So a beta particle is basically a fast-moving electron emitted from the nucleus of an atom undergoing radioactive decay. So basically it's giving off an electron, and we know electrons, they don't count for the mass, right? So is there going to be any change in mass? Probably not. But what's happening here that's strange, you have to remember when we talked about how protons and neutrons are made of smaller things. So what's happening in beta decay is one of the neutrons, so which was neutral, so it had a positive and a negative piece to it, is becoming a proton. So its positive piece is staying there, but the negative electron piece of that neutron is leaving. So the mass isn't going to change, but the thing is going to gain a proton. So let's see what that looks like. For beta decay, the nucleus has one less neutron, but one extra proton. So the atomic number, that Z, is going to increase by 1, but the mass will stay the same. So let's take a look at this. Oh man, that O should be up here. I don't know why it goes wacky when I go into different modes, but so here's your polonium. You have a beta particle that leaves, which doesn't affect the mass. Here's the symbol for a beta particle. Notice the 0 on the mass because it doesn't change. You might wonder why the -1 here. That's going to be more obvious when we get into the equation, but this is the beta particle symbol. Notice mass didn't change, but it went from 84 to 85. You gained a proton, right? So it's no longer PO, it's AT. Now, here you can kind of see where this -1 comes in. So here's again the skeleton equation. If I gave you Y, you should be able to solve for X and vice versa for a beta decay. So in this case, you got your polonium. Now, look at the numbers. Again, everything on this side should add up to this side. So why the -1 here? Because 85 plus -1 gives you 84. So that helps us balance things out by writing the symbol with the -1. And 0 on the mass. So 0 plus 218 gives you 218. So these all add up to be whatever goes here. So the equation is A, and A here, because nothing changes. Z, and this is Z plus 1. So Z plus 1 plus or minus 1 is Z. That's beta decay. So, oh gosh darn it. this H should be up here. I thought I fixed all these. 234, not going to change, right? So 234 is 234. 90 goes up 1, remember, in beta decay to 91. So now it's PA instead of TH. All right, this one, here we go. So we don't know what this was. We go over here and we say, well, it was beta decay, so the mass will be the same. So 210. But PB, right, has 82 protons, but 82 minus 1 gives me 81 protons. So TL is the element that goes there. Again, just more examples at this point. So how do I predict what goes here? The mass is not going to change. So 210, 83 plus 1 gives you 84 for this one. And then you look up what 84 is, and it's polonium. And more of the same. Again, let's talk about gamma decay. So gamma rays are not charged particles like alpha and beta particles. They are really just part of the electromagnetic spectrum. So think like X-rays, only they're more dangerous than X-rays. They have more energy than X-rays do. So gamma rays are electromagnetic radiation with really high frequencies. When atoms decay by emitting alpha and beta particles to form some new atom, the nuclei might still have too much energy to be stable, so it may emit some gamma rays as well. So excess energy comes off as gamma rays. So let's talk about these different particles and their penetrating power and their sort of danger to us. So an alpha particle, again, it's sort of, as atomic particles go, it's a big chunky thing. It's a helium nucleus. Has a charge of +2. It is easy to stop, okay? So penetrating ability is low. If you had a piece of paper, it would be enough to stop an alpha particle. So these, if you're wearing some clothing, you're safe from alpha particles for the most part. Beta particles, on the other hand, are like electrons, so they're much smaller. So you might think, well, it could get through a piece of paper. Then you're right. But it has a -1 charge. It can be stopped by having clothing. So if you have like a hazmat suit on, you're good probably for beta particles. Now the gamma radiation, on the other hand, this is really high energy. It's not a particle. So again, think like an X-ray. It will go through your body. It would take lead to stop it. And the problem with that is as it goes through your body, it can go through your cells. It can break DNA chains in those cells. And then when that cell goes to reproduce, it could make bad copies of itself, which we think of as cancers. So other types of nuclear reactions that you should have heard of before now: nuclear fusion and nuclear fission. So think like fun in the sun. This is what's happening. Fusion is what's happening in the sun. So you have two smaller atoms being combined together to form something larger. So two hydrogens becoming a helium atom. This is where all those big things on the periodic table are made. So stars, our sun right now is fusing hydrogen into helium. Later on in its life, it'll turn helium into bigger things like oxygen, carbon. And if it's not big enough for this, but if it were big enough to go into supernova phase, then it would make even bigger things like gold and, the things further down on the periodic table that are harder to find. So nuclear fission, on the other hand, this is what's happening in nuclear power plants, where you have one atom and you're splitting it apart. So not just the natural decay that we've been talking about with alpha, beta, gamma, but forcing them apart. So hitting it with some particles to force it apart. And the last thing we need to talk about here is half-life of radioactive atoms. So everything has a really specific half-life. This could be a whole lesson in itself, how to calculate half-lives. But the quick version of it is you can time things like atomic clocks go by the half-life of specific atoms. So you can time things, you can see how old things are. When you say, oh, how do we know how old the Earth is? It's because we've taken rocks and we've looked at the radioactive decay, those radioactive elements that have been decaying for years and years, see how much is left from what would originally have been there, and figure out how long it's been. So everything, a half-life is the time it takes for half of the material to decay. So if something's not gone through any half-lives, it has the whole thing. If it's gone through one half-life, half the material's gone. If it's gone through two half-lives, 1/4 of the material's gone. If it's gone through three, you got 1/8. So you can use these calculations if you know how long the half-life of something is to figure out how old it is. So we might take that up a little bit later. Like I said, that's a whole other lesson. Here are some examples of some half-lives. So for sodium 24, the half-life's only 15 hours, right? Some of them have seconds. Their half-life is just 60 seconds. And some of them are very, very long, like uranium 238's half-life is 4.5 billion years. So stuff isn't going anywhere for a while. And this is why when we have nuclear waste from nuclear power plants and it has really long half-lives, we have to think about, well, where are we going to store this if it's going to be around and dangerous to people for so long? All right, I'm going to end this here. Good luck.